Alright, so here we go, doing question number 28. And so the idea is do more than 50% of US adults feel they get enough sleep. So I like highlighting these types of problems. And so the do more than 50% of US adults feel they get enough sleep. This is the research question, okay, which is really nice. And so here, the more than gives us an idea of what our alternative hypothesis is going to be. I'm going to scroll this down just a little bit. Oops, too far. All right. And so this is going to be our alternative hypothesis. Okay. Do more than 50%. So this 50% right here, this is our P. We think that 50% of U.S. adults, wait a minute, of U.S. adults, that's going to be our population. So POP for population. Feel they get enough sleep. Feel they get enough sleep. This is our trait. Okay? So what we're looking at is I'm thinking 50% of US adults feel they get enough sleep, and then my alternative would be do more than 50% get enough sleep. Alright? So now, according to Gallup's December 2004 lifestyle poll, this 55 right here, okay, this 55 right here, this is going to be our P hat. So I'm going to draw a little, oh no, arrow over here. This is P hat, and it's 0.55, okay? And again, it's the same population of U.S. adults said that they get enough sleep. There's the trait again. The poll was based on a random sample. The random sample is super important. I'm going to highlight that because a random sample is one of our assumptions that we're going to look for. Of 1,003 adults. So the 1,003 adults, this is going to be our sample size, and equals, and again, U.S. adults is our population. And now they want us to test an appropriate hypothesis and state your conclusion. And so now we're into the four-step process, right? And step number one of the four-step process is state the hypothesis, all right? And what we're going to do is we're going to do that in symbols and in words. So obviously I need a null hypothesis, and the essence of the null hypothesis is no change. And so that means my P is going to be equal to the 0.5, because I do have to report it as a decimal, not as the percent that's up here. And I know that my P is equal to 0.50. That's what I'm going to assume is true. Then my alternative hypothesis is going to be P is greater than, is more than, from right here, the 0.5. And that's the research question. Okay, so if this is in symbols, what this means is the proportion, because that's what P stands for, a proportion, of what? Of the population. And what's my population? Of U.S. adults, right? With what trait? Feel, they have this trait, feel they get enough sleep. Is, that's the equal sign right here, 0.5, and the 0.5 just goes on the end. I know I'm running uphill. It's been a while since I've recorded these videos, so just bear with my stylus here. Alright, so then what's the alternative? Well, the alternative hypothesis is the proportion of U.S. adults, that feel they get enough sleep is more than, to use that research question word from up here, more than, and I'm going to scroll this over just a hair, more than 0.5, right? So that it stays in the picture. Alright, and that makes us happy. So there it is in symbols and in words. Okay? So now what's the second step? The second step is to check the assumptions for the normal model. because I'm hoping in an introductory stats class that it's going to fit the normal model, because that's basically the only model that I have. So I need to check the assumptions for the normal model before I can go forward. And so the first one of those assumptions is it random? Is it independent? Okay? And is it random and independent? Well, it is a random sample, and so I'm going to assume that with a random sample being done by Gallup that it is also independent. So that makes me happy. 2, of course, is the less than 10% of the population. And so if I throw a 0 on here, I get 10,000 U.S. adults. There are certainly more than 10,000 U.S. adults, so that assumption is met. All right, and then the third thing that we're going to look at is our sample size. All right, and the first part of that is n times p has to be greater than 10. Okay, and so I do have that my n is equal to 1003. So I have 1003. My p is equal to 0.5. And of course that's equal to, well, half of 1,000 is 500, half of 3 is basically 1, so you're going to make it 2. So you get 502, okay, which is definitely greater than 10. Excellent. And then I am going to scroll over one more time, okay, and what is my fourth thing that I want to check? And the fourth thing that I want to check is the other sample sizes, n times 1 minus p has to be greater than 10. Now, my n doesn't change, which is nice, okay? So I still have 1,003, and now you're going to have 1 minus 0.5 has to be greater than 10. Now, 1 minus 5 is also 0.5, and so you're going to get 502. You should round this one down, 501. So that's also greater than 10, okay? And so this assumption is also met, and that makes us very happy. Okay, because now the assumptions for our normal model are met. I checked my assumptions, they're going to work. So now if I can use my normal model, the third thing that I want to do, oh crumbs, I picked the wrong color. You can't see it, but I'm picking the wrong color. Alright, here we go. So step number 3 is draw and calculate. Alright, so for draw and calculate, I want to draw the normal model. Oh, I thought this was going to look terrible, but it actually doesn't look too bad. I'm really not used to using the stylus for this. Alright, so there it is. I've drawn the normal model, the normal distribution. What goes in the center? What always goes in the center is my null hypothesis. My null hypothesis here is p is equal to 0.5. So here is my 0.5 in the center. Now typically what I do is I mark off 2 standard deviations to the left and to the right to get an idea about what would be unusual, especially with the normal model. All right, I know that 2 standard deviations away is that. Okay, so I need to calculate my standard error here. My standard error is going to be equal to the square root of p times 1 minus p all over n. Alright, and so now I'm going to have the square root of 0.5 times 0.5, okay, all over 1003. Okay, and so now I need to plug this into my calculator. So here we go. The square root button is right here, so you got second square root 0.5, right, times 0.5. Now, you know what? Here, let me do it this way. It's 0.5. You should really put the parentheses in here with the 1 minus 0.5. Okay, I was just going to shortcut that step, but for other problems, you know, you want to make sure that those set of parentheses are there. So let me not leave them out here. And then you've got 1003, and that is in the denominator also. Now I am done, so I don't have to worry about tabbing out from underneath. All I have to do now is hit enter, and it tells me that my standard error is 0.01623 decimal places. Okay, so I got 0.01623 decimal places. 0.016. And so now I just need to take 0.5 plus 0.016, which is going to give me 516. Okay, and so that's what's going to go right here, 0.516. And then I have to take 0.5 plus 2 of those standard errors, 0.016. And that's going to be equal to what, right? Because now I'm 2 standard deviations away. 2 standard deviations away. Where's my calculator? There it is. Okay, so in la calculator, I got 0.5 plus 2 times 0.016. And I hit enter, and I've got 0.532. Okay, so 0.532. And so that's what's going to go 532 right here. Now I also have to go this way, and so now I need to subtract. So now I'm going to have 0.5 minus 0.016, okay, for 1 standard deviation away. So you got 0.5 minus 0.016, and that gives you 0.484, okay. So now I go over here, 0.484, and that's going to go right here, 0.484. And now I have not 1, but I have 2 standard deviations away. So now I'm going to subtract 2 of those standard errors away. Okay? And so now you've got 0.5 minus 2 times 0.016. And that gives you 0.468. Go over here. 0.468. 0.468. Okay. So that gives me that. Now what you want to do is put your test statistic in. Remember I told you that p hat was 0.55? What you want to do is take that p hat of 0.55 and you're going to mark and shade. Okay? So now remember you are looking for more than 50%. So I'm going to go up here and look, 0.55 is actually greater than this, right? So I'm somewhere over in here, okay? Here's my 0.55, somewhere past 0.532, and more than is this direction, so I'm going to shade to the right, okay? Now, there is a way to do it with just this and the standard error, but basically what we've been doing in class is now we calculate a z-score that goes with this. And remember, the z-score is the value of your sample minus your center, which is usually your null hypothesis, divided by your standard error on the bottom. So the value I have is 0.55 minus my center is 0.50. I've got that from right here, okay? The value came from my p hat right here, and my standard error is 0.016, and that comes from right here. Now I need to type this into my calculator to figure out where it's at. This is where a lot of students sort of mess up, okay? You want to have the 0.55 minus the 0.5 in parentheses so that the subtraction is done first, and then divide it by 0.016, okay? And that gives you the correct answer of 3.125 standard deviation. Now if we look over here, right, hold on. If we look over here, look, I am 1, 2, looks like 3 and maybe a little bit more standard deviations away. That makes sense, right, that my value over here, oh, I gotta change views. Sorry, I just forgot to change my pen. It makes sense this is going to be 3.125 away. That makes me happy, okay? But here's a lot of times what I see happen. I see students go 0.55 minus 0.5, right, divided by 0.016, and they hit enter, and they get negative 30.7. Okay, that's a negative 30 standard deviations away. That's a zillion miles away. In fact, it is, let's go ahead and draw this with a red line. This is minus 1, this is minus 2. Minus 30 is so far over here, it makes us really sad. Okay? That answer doesn't make any sense. And this is why we draw. okay, our picture. So that if we fat finger something, if we enter something into our calculator wrong, we have a sense of what the right answer should be. And that makes us very happy. Alright, so be careful with your parentheses in this particular problem. Now that means that this is a z-score of 0.3125 away, and I'm shading this direction. Okay, so now what I'm ready to do is I'm ready to find I'm going to scroll up just a little bit, okay, so that you can keep the 4 steps in view. Okay, but what I need to do now is I need to do my p value. I need to calculate my p-value. To calculate my p-value with the normal model, okay, up here, see the normal model, I need to use a normal CDF, alright? And the calculator is always going to shade, alright, from left to right. The calculator is always going to shade from left to right. It's always going to calculate that probability from left to right. So I need this lower score to go in first, 3.125. I need an upper score, something that's over here to go in. Well, if I go over here, I'm like 20, 30, 40. This thing is getting so small that really what we use is 100. Because at 100, the tail is so close to the x-axis that there's basically no probability in between. And so that's probably much close enough. Alright? And this is a one-tailed test, so the p-value is just going to be this single number that I get right here. And I do need my calculator for that. So I'm going to open up a calculator, right? And so here's where I'm going. I'm going to second distribution, because I'm using the normal distribution. Normal CDF, you'll see is number 2. I'm going to put my lower bound in, is going to be 3.125. And, oh crap. Enter. My upper bound is going to be 100, you know, or 1 million, or whatever it is your professor wants you to do. In our class, we use 100. Mu is 0, right? Because this number of standard deviations at the center is 0, and the standard deviations is 1, right? This is 1 standard error, 2 standard errors. This is 3 1/4 standard errors away, so my standard deviation is 1, right? And so now all I have to do is hit enter, and enter again, and I get this. All right. Now, I have seen a lot of issues with this. You get this 8.89, and all of a sudden, over here, I see, oh crap, where did my pen go? 8.89 as a p-value. This makes me very sad, okay? A p-value of that is going to make me very sad, because p-values go from 0 to 1, where 0 is cannot happen, and 1 is must happen, will always happen, okay? And so a value of 8.8 is nowhere in this range, and so that's why it makes me sad, and I start crying when I see this stuff, because it means students don't understand what's going on. Alright, so now let me erase the bad part. Alright, all this little red stuff, because I don't want to be sad. Alright, I'm actually going to erase that right there, okay? And now let's go ahead and put the right number in. Basically, this E with the -4 means I actually have to move the decimal place 4 in the negative direction. Alright? And so I'm going to end up with 8.89, and I'm going to move it 1, 2, 3, 4 decimal places over. Oops, crap, I pushed a button. Alright, so there's where my decimal place goes, and I need 1, 2, 3 zeros as placeholders. This number is very, very different. Now let me clean it up so that we can look and see what it is. Alright, so let me, oh, there, need to get rid of that. And that decimal point right there. Oh crap. Let's put the 8, 9 back in. Okay, so this is tens, hundreds, thousands, 10,000. So you're basically looking at about 9 10,000ths. So 9 out of every 10,000 samples are going to be this far away if the null hypothesis is true. It's a pretty tiny, tiny, tiny p-value. Alright? And so that allows us to go ahead and, let me go ahead and scroll up just a little bit more. And I'm going to take this right here and just kind of drag it down out of the way. Alright, so that we can finish drawing here. Alright. And so this brings us to step number 4, right? We're going to state the conclusion. And to state the conclusion, what I'm going to do is compare my p-value to my alpha, right? Alpha is going to get compared to my p-value. And here, it doesn't say, so I'm just going to use an alpha of 0.05 because that's our default. Usually this is the default alpha when it doesn't say. My p-value is 0.00089, and now I have to determine, is 5.05 larger than 0.0089, or is 0.0089 larger than 0.05? And of course, this is much, much bigger. Okay? Much bigger. This is almost 0 over here. Okay? So now, if your alpha is larger than your p-value, you are going to reject. I need to see in there. The null hypothesis. Alright, so let's go ahead and write it. So we reject that. And here, you basically, this is just the null hypothesis. And this is why we write it in words. So let's scroll up and see what we wrote for that. Okay. The proportion of U.S. adults that feel they get enough sleep is 0.5. So that's what we're going to write here. We reject that. The proportion of U.S. adults that feel they get enough sleep is 0.5. And then the other part of that is we have, right, if you reject, you have strong evidence for the alternative hypothesis that the proportion of U.S. adults. Now I'm starting to go off the screen, so I want to scroll this up a little bit more. That the proportion of U.S. adults that feel they get enough sleep is greater. I guess I should use more than is greater than, because that was what I wrote in the alternative hypothesis. I apologize. Is greater than 0.5. And then of course you always want to have your p-value stated. I know that at least in the stats book we use, it just says p here, but p is really the population proportion. You should really write out p-value so that people aren't concerned. And you want to state the p-value because this gives the audience who's reading this a chance to understand how strong your evidence is. How strong your evidence is based on this tiny little p-value right here. So you always want to state that, right? And that's your conclusion. I know this has been a really long video, but I did go step by step through each of the calculations in the 4 steps. So hopefully this gives you a really nice idea of how to do a hypothesis test for a single sample proportion, and that makes us really happy. So until you watch my next video, have a great time with math.